Watch the complete playlist on the app Pions. Download the app now.
Okay, let's start with question number 1. It says, find the equivalent capacitance of the combination of capacitors between the points A and B as shown in the figure. Also calculate the total charge that flows in the circuit when a 100-volt battery is connected across point A and B. So I hope this is clear to all of you. This is our diagram, okay, circuit diagram of all the capacitors which are connected like this. Let's see which one are in series and which one are in parallel. Okay, so first of all, when just imagine that current or the charge is like water. So if you allow the water to flow like this, okay, this water is getting splitted over here, right? If this is one pipe and this is another pipe, okay, the water will get splitted over here. Since the water is getting splitted at this junction, we call it as junction. In the next chapter, we will call it as junction. So this point, okay, here this part and this part, okay, they are parallel, okay, they are parallel to each other. So here the same water is flowing like this, okay, no matter it looks like this, but the same water because it is not going anywhere. So here the same current is flowing here, okay, or charge is getting stored across the capacitor. So this 60, this 60 and this 60, they are in series. Let me repeat again, 60, 60 and 60, these three are in series. Let's find the equivalent in series. So 1 by C equivalent in series will be equals to 1 by C1 plus 1 by C2 plus 1 by C3. This is the formula for 3 capacitors in series. Now what is here? C1, C2, C3 all are 60. So let me write here 1 by 60 plus 1 by 60 plus 1 by 60. Sir, you didn't convert this into microfarad? No, I will convert this microfarad into farad at last when we will find the charge. Okay, to find the capacitance, anyways the final answer will be in microfarad, so no need of putting 10 to the power minus 6 and getting confused, right? So 1 plus 1 plus 1, this will be 3 by 60 over here, that is 1 by C equivalent. So this implies C equivalent of the first branch is 60 by 3 sorry, and that is 20 microfarad, right? So let's redraw this diagram. Let me draw here. This is over A, this is point A, and from point A our 40 microfarad is going over here. This is 40 microfarad, and from 40 microfarad 1 is going like this, okay, and let's call this as a C point, okay, and this point as D. So at point C there are 2 wires which are going. One is I am drawing like this, okay, and one is I am drawing like this, okay. So this is our point C. The upper branch had 3 capacitors which I have solved just now, and I can write, instead of these 3, I can write a single capacitor of 20 microfarad. So this will be 20 microfarad over here, and the below one, the below wire which is going from C, that will be 10 and 10 in parallel. So let's make here again 10 and 10 in parallel, and they both are connected here, and this is connected across point D, and that point D is further going across point B. Clear? So this is 10 microfarad and this is also 10 microfarad, right? So our circuit gets simplified like this. Now now let's see this 10, 10 and 20. All 3 are in parallel, as you can see, because 20, the resultant is parallel in 10 and 10. So resultant of these 3 across CD, so C equivalent across CD will be equal to 20 microfarad plus 10 microfarad plus 10. We can directly add them. Why we can directly add them? Because they are in parallel. So 20 plus 10, 30, 30 plus 10, 40. So this is our 40 microfarad. Done. So let's redraw between A and B. We already have one with 40 microfarad. Another one we got just now with 40 microfarad between A and B. Let me repeat again. Our C and D, we got it as 40. Now 40 and 40, they are in series. So what will be our C equivalent in series? So across AB, the equivalent capacitance, this is across CD, okay. Let me write here across CD. So AB will be 1 by C equivalent, that will be equal to 1 by 40 plus 1 by 40. And 1 by 40 plus 1 by 40, 2 by 40. So let's go down here. So C equivalent will be equals to 40 upon 2, which is equals to 20 microfarad. I hope this is clear. So the whole circuit, this whole circuit can be written as a single capacitor with 20 microfarad. That is called equivalent. Let me remind you once again, equivalent means all those capacitors which are joined in this particular fashion can be, said equivalent to this. Sir, what is equivalent? Same. They both are same. So even this whole circuit is giving 20 microfarad capacitance and even this single capacitor. So either you join a single capacitor with 20 microfarad capacity, or you join so many different capacitors in this particular fashion. Clear? So this is A and B capacitance. Now let's read the question once again. Find the equivalent capacitance of the combination. We found it as 20 microfarad. Now also calculate the total charge flows through the circuit. When you are finding the charge, you have to get it in a standard unit. So we know that our charge across the circuit can be found as Q equal to CV. Correct? Now what is the equivalent capacitance here? 20 microfarad. Be very careful. You have to convert it into 10 to the power minus 6. That is farad. You have to get it. Because standard unit for charge is coulombs. That is only if 1 farad multiplied with 1 volt, that gives you 1 coulomb. That's why you have to convert this into farad into 100. So this will give us 2000 or 2 into 10 to the power minus 3 coulombs. That's your charge which is flowing in this whole circuit. Be very careful, since the question is saying what is the what is the charge flowing between AB. This is the charge. They have not said what is the charge across each capacitor. That will be different. So across each capacitor it will not be 2 into 10 to the power minus 3. This whole circuit it is 2 into 10 to the power minus 3. For individual it can be 2 into 10 to the power minus 3 like in this case, and for other cases like this branch and this branch, the charges will get splitted. Done. Okay, great. Let's move to question number 2. Question 2 says 4 capacitors are connected as shown in the figure. Calculate the equivalent capacitance across X and Y. So we have to find the equivalent capacity along X and Y here. Be very careful, there is nothing connected here across this wire. Okay, so if this is simply a wire, there is no capacitance of a single wire. Okay, because there is a capacitance for a capacitor, so this wire doesn't take into account any capacitance. But be very careful with the connections. How this wire is connected, that will decide many things, right? So X and Y, let's keep it as it is and let's try to simplify it. Let's make it as A, B, C, D. Okay. So first capacitor is connected across AB. Let's join this point A. Let's call it as A. I'm trying to redraw this. A, B. Across A, 2 microfarad. B, AB across AB, 2 microfarad, right? Now another wire which is connected from A and C. So basically listen very carefully. This C point and A point, they are short. You can say that A and C both are same point, right? Why same, sir? Because A and C, they are connected with the same wire. Okay. So A and C will be at the same point. So you can say that another wire which is 3 microfarad, that is connected between C and B. So C and B means C is nothing but A and B. So that can be drawn like this here. 3 microfarad like this. Now you will say, sir, how can I justify this thing that C and A are same? Okay, fine. Then let's call this as C. Great. I hope this is clear. So C and this I am connecting B, C here. So let's say that this wire, this is nothing but this wire. Nothing in between A and C, right? So if there is nothing, then you can say this as C, you can take this as C, you can take this as C, doesn't matter. I hope this is clear. So C and A are this point. So let me remove this, and to avoid any confusion, this is like this. Now from one end of the B, one wire is going across D, correct? And across this D, one 5 microfarad is connected, whose one point is across C. So that C, let's call this as C. Let me remind you once again, this is our C. And one end is across C and another end is across whom? Across D. And that D is connected across B. So same thing. Okay. You can call this as C, you can call this as D, and this is our 5 microfarad. Correct. Let me repeat again this whole scenario. Pay attention once again. A and B, across AB you have one capacitor of 2 microfarad. Yes? Is it same? Yes. Between the two ends of A and B you have this. Across C and D, now from C, look at the C wire. Look at this C wire. One wire is going across A. Is it going across A? Yes sir. From here it is going across A. Great. From C, one wire is going across the other end of 3 microfarad capacitor. Yes sir, this is going over here. Same thing. And other end is going across 5 microfarad capacitor. Yes sir, this is going across 5 microfarad. Which means this is correct. This diagram is correct. Our wires are connected perfectly. Let's talk about wire D junction or D junction. There are 3 wires. One wire is going across 5 microfarad, which is this one. From D across 5 microfarad. And from D, one wire is going across B. Exactly, it is going across B from here. And one wire is going from D to 10 microfarad. Okay. Okay. So we left with 10 microfarad. Let's write here D and let's draw this 10 microfarad over here like this. Okay. Now you will say, sir, this is our Y. So where to keep X? This along this AC wire, you can put anywhere X. It doesn't matter that much. So let's take it from here only. Okay. Just to keep the consistency of our diagram. So let's say from A, this is our X, right? Okay. I hope this is clear. Great. So from D, one wire is going across 10 microfarad. This is 10 microfarad and those are in 3 in parallel. So if this is 2, this is 3 and this is 5. Okay. Let's solve this circuit and find the equivalent capacitance. So C equivalent will be equals to 2 plus 3 plus 5. So that is equals to how much? 10 microfarad. Sir, why you directly added? Because it's a parallel combination of capacitors. In parallel combination of capacitor, the equivalent capacitance will be the sum of individual capacities. Right? So let's redraw between A and D. So between A and D, our capacitor is 10 microfarad. This is our end A, which is going further to X. And this is our end D, which is further going to 10 microfarad and which is connected further to Y. Now 10 and 10, they are in series. So let's find C equivalent across XY. So 1 by CXY, that will be equals to 1 by 10 plus 1 by 10. So that will be equals to 2 by 10 and 1 by CXY. So C equivalent across XY will be equals to 10 by 2, which is equals to 5 microfarad. Done. That's our complete answer to this question. I hope this is clear. Let's move to question number 3. Question number 3 says, calculate the capacitance of the capacitor in the given figure. If the equivalent capacitance of the combination across AB, let's write here AB, is 15 microfarad. So equivalent across AB is 15. It's given already. C equivalent across AB is 15 microfarad. Now let's call this as any point XY. This is X and this is our Y. So what will be our equivalent across XY? CXY, that will be equals to, now both are in parallel. So parallel will be 10 microfarad plus 10 microfarad. So that will be equals to 20 microfarad. This will be our CXY. Let's redraw this diagram. So this is our 20 microfarad and this is our C capacitance, unknown capacitance. This is A and this is our B. Let's find the total. So equivalent in series will be 1 upon C equivalent will be equals to 1 by 20 plus 1 by C. Now what is C equivalent? So C equivalent is given as 15 microfarad. So 1 by 15 equals to 1 by 20 plus 1 by C. This we can further solve it as 1 by C equals 1 by 15 minus 1 by 20. Correct? And this implies 1 by C equals, let's take the LCM. It will be 300, 15 twos are. So it will be 20 minus 220 into 15. Correct? Or you can cross multiply, whatever you can. So 20 minus 15 is how much? That will be giving you 1 by C equals to 5 by 300. Correct? And this will give you C value as 300 by 5, which is 60 microfarad. Done. This is our complete answer to question number 3. Okay. Let's move to our question number 4. Question number 4 says, calculate the equivalent capacitance between the points A and B of the given circuit. Clear? So let me repeat again. If this is the water which is flowing through the pipes, imagine capacitors are houses and this is the water flowing through it. So if this is the water flowing, this water will have probability of splitting at this point. At this point it will split. Okay. And since it is getting splitted, the same water is going across here and here. So which means this C2, C3 and C4, they are in series, and C6 and C5 are in series. The resultant of both will be in parallel. So let's solve this. So first of all, 1 by C equivalent, that will be equals to, let me write here point as X and Y upper branch. Okay, upper branch will be 1 by C2 plus 1 by C3 plus 1 by C4. Now C2 is how much? 4 microfarad. C3 is how much? 2 microfarad. And C4 is how much? 4 microfarad. So let's write here 4 as our common LCM. 1 plus 2 2s are 4 and 1. So it will be 2 plus 1, 3, 3 plus 1, 4. 4 by 4 you got. So 1 by C equivalent here you got as, okay, 1. So C equivalent will also be 1 microfarad. Okay. Let's redraw this diagram. So redrawing this diagram will be C1 as it is 4 microfarad. Upper branch will be 1 microfarad. Just now we found it. And lower branch will be 4 and 2 microfarad. This is 4 and 2 microfarad. Correct? So this is A and this is B. I hope this is clear up till here. Now the lower branch here, let's solve this. So this will be again series. So series combination of this equivalent will be 1 by C equivalent will be 1 by 4 plus 1 by 2. So this will give us here 4 as our common LCM, 1 plus 2, 1 by C equivalent. So this implies C equivalent will be equals to 4 by 3. 2 plus 1 is 3, and when you reciprocate you got 4 by 3. Let's redraw this whole circuit, okay, over here. So our at point A it was how much? 4 microfarad, as you can see in the diagram. Correct? Upper branch we got 1 microfarad, the equivalent, and the lower branch we got 4 by 3 microfarad. That's our equivalent capacitance. Correct? So now this is B. Let's simplify these two, and these two will give us the equivalent as, since they are in parallel combination, 4 plus 4 by 3. So when you cross multiply, it will give you 12 plus 4 upon 3. That is 16 by 3 microfarad. Done. So here from point A, 4 microfarad, and here it is 16 by 3 microfarad across B. Now this is A, this is B. Let's find the series combination to get the equivalent of the whole thing. So from series combination, 1 by C equivalent across AB. Let me just write here across AB. Across the whole circuit AB, 1 by C equivalent will be equals to 1 by 4 and reciprocating 3 by 16. So this will give us 16 over here as the common LCM, 4 4s are and 3, 1 by C equivalent. And this implies the whole circuit has an equivalent capacitance of 16 upon 7 microfarad. Done. That's our answer to this question. Let's move to question number 5. Question number 5 says a network of 4 capacitors, each of 12 microfarad. Let's put here 12 microfarad. This is also 12 microfarad. This is also 12 microfarad. And this is also 12 microfarad, connected to a 500 volt supply as shown in the figure. So here this is a battery giving 500 voltages. Determine the equivalent capacitance of the network and charge on each capacitor. This time they are not asking charge across the capacitors. No, they are saying charge on each capacitor. So you have to be little careful, right? So first of all, let me remind you once again, C1, if you allow the water to pass through this water will get splitted across the upper branch, and the same water will go across C1, C2 and C3. While the water which is getting splitted here, C4, will be in parallel to the above circuit. So let's first find the above circuit. So for above circuit, okay, so for the equivalent of C1, C2 and C3, it will be 1 by C1 plus 1 by C2 plus 1 by C3, correct? Okay. Now this will give us how much? This will give us C1 is how much? 1 by 12 plus 1 by 12 plus 1 by 12, which is how much? 3 by 12. And 3 by 12, which will be equals to 4. So C equivalent for the upper branch is 4 microfarad. Be very careful. So let's redraw from this point, upper branch 4 microfarad capacity, lower branch how much? 12 microfarad capacity, correct? And this is going across circuit A, B. This is our AB where our battery of 500 volt is connected, right? Now they both are in parallel. If they both are in parallel, the equivalent of these two will be, C equivalent will be 12 plus 4, which is 16 microfarad, correct? 16 microfarad capacity. Now this is the equivalent of the whole circuit. So let's redraw this whole thing, okay? 1 second. Over here. Let me draw it here. So this will be our 16 microfarad, correct? Whole divided, okay? Whole here with connected here with 500 volts. Great. Now, first of all, if here this is our 500 volt, okay, or look at the second diagram, then the 4 microfarad and 12 microfarad, they both will have the same voltage, right? Because they are in parallel. If they are in parallel, then voltage across the upper branch will be same as the voltage across the lower branch, which is 500 volt. So first I will find charge, which is the total charge going into the circuit. So first answer over here we got as 16 microfarad. And let's solve for the charge. So charge here, let me solve it this side, second one. Q is equals to CV. Now what is C? 16 microfarad. Now you have to convert it into farad. And voltage 500. 16 5s are 80. So 8000 means 8 into 10 to the power minus 3 coulombs. Listen very carefully. This 8 into 10 to the power minus 3 is going across this whole circuit, across this 16 microfarad. So here it is 8 into 10 to the power minus 3 going across this. Total. Is it same across the upper branch and the lower branch? No. It will get splitted. Here it will go few and here it will go few. But whatever few it is going on the top branch, that will be same across all the three because they are in series. but that will be completely different from the lower branch. Let's see how. Since the voltage of the upper branch is 500 and the lower branch is also 500, let's find the charge across the lower branch. So charge across this 8 into 10 to the power 3 minus 3 is not across each capacitor, it is across the whole circuit. So charge across C4. What is the voltage across C4? Sir, 500 volt. And what's the capacity? 12. So let's find the charge across that. So voltage is 500 and capacity is 12. So 12 into 10 to the power minus 6. Correct? So let me call it as Q4 into, what is the voltage? 500. 12 5s are 60. So 6 into 10 to the power minus 3 coulomb. We got this as Q4. If out of 8 into 10 to the power minus 3 coulomb, if 6 into 10 to the power minus 3 is going across C4, what is going up in the upper branch? Across, charge across C1 will be equals to how much? 8 minus 6. Let me repeat again. If 8 liters of water is entering at that point, out of which 6 liters of water is going here, then how much water is left for the upper one? 8 minus 6, which is 2. And since all of them are connected to the same pipe, water will be same. So 2 across each. So across C1, Q1 will be 2 into 10 to the power minus 3 coulombs. This is our Q1. Let's call it Q2 will also be 2 into 10 to the power minus 3 coulomb. Same, because they all are in series, and Q3 will be equal to 2 into 10 to the power minus 3 coulombs. Done. So this is the charges across each capacitor, Q1, Q2, Q3, Q4. Yes, let's move to question number 6 now. Question number 6 says, two capacitors of capacitance 3 microfarad and 6 microfarad are arranged in series and are connected in parallel with a third capacitor 4 microfarad. So let's try to draw this. So first one is C1 and C2 are connected in series. So let me draw here C1 connected in series with C2, C1, C2, okay, and are connected in parallel with C3. So parallel with C3, like this the diagram will be, okay. The arrangement is connected across, this whole arrangement is connected across a 6 volt battery. Great. Question says, calculate the total energy stored in the capacitors. Now listen very carefully. The question is saying calculate the total energy stored. They didn't say about individual. If they'll say about individual, the procedure will be different. So read the question very carefully in the board exams also. If they are asking for individual charges, individual voltages or individual energies, or if they are asking about the system. To find about the system, first we have to find the total capacitance, right? So C1 here is 3 microfarad. So 3 into 10 to the power minus 6. 6 into 10 to the power minus 6. And 4 into 10 to the power minus 6. We will not use of this 10 to the power minus 6 while finding the equivalent, right? So what will be C1 and C2? They are in parallel. So let's redraw this. Okay, we will draw this again. First let me find 1 by C equivalent will be 1 by 3 microfarad plus 1 by 6. I am not using 10 to the power minus 6 because anyways you will get it in microfarad only. So 6 here. 3 2s are 6 1s are. So this will be 3 upon 6. So C equivalent will be here 6 by 3, which is 2 microfarad. So let's draw the diagram again. Yes. So let's draw it again. So here it is 2 microfarad and 4 microfarad. So 2 microfarad and 4 microfarad. 2 and 4, and they are connected across a 6 volt battery now. So our equivalent of the top one was 2. Now 2 and 4, let me write here microfarad so that we don't forget it at the end. So 2 and 4, when they are connected in parallel, the parallel equivalent will be straight away 2 plus 4. 2 plus 4 will be 6 microfarad. So let's here redraw this diagram that this whole circuit is simply giving the equivalent or the net capacitance as 6 microfarad. Here it is 6 volt. So if this is the capacitance, this is our voltage. What is the energy stored? Sir, energy stored will be energy stored will be half CV square. This is our formula for energy stored. So half, what is C? So C here is 6 and voltage here is how much? 6 square. Sir, what about microfarad? Yes. So you can write it as 10 to the power minus 6. Correct? This 6 has 10 to the power minus 6 there. So this will be 2 3s are 36 into 3. So this will be 36 into 3 microjoules. We can write this 10 to the power minus 6 as microjoules. So 3 6 are 18, 108 microjoules. Done. That's your answer. This is the total energy stored in the whole system of these capacitors. And let's move to our next question. Question number 7. Question 7 says a 800 picofarad capacitor is charged by 100 volt battery. So there is first capacitor C1, that is 800 picofarad. In case if you don't know what is pico, it is 10 to the power minus 12. You have to remember these things. Okay, very commonly used in capacitors. So 800 picofarad, pico means 10 to the power minus 12 farad, is charged by a 100 volt battery. So voltage here is 100 volt. Great. After some time, the battery is disconnected. The capacitor is then connected to another 800 picofarad capacitor. What is the total energy stored? Okay. Now listen very carefully, because this is quite important question. Here we will make use of a very important concept also, like law of conservation of charge, okay, and what is common potential. We will see that also. What is happening here is we are charging a capacitor, okay. Let's say this is our capacitor, okay. I am charging it with a battery. So this is one wire, this is another wire, and I am charging it with a battery. Once it gets charged, I'll remove the battery. So now the charge gets stored here inside this, okay. Let's call it as first capacitor. Okay, what happened? One second. Okay. So this is our first one. And first one, once it gets charged, now I took the first one. It has charged now. Now it is connected to another capacitor. Okay. Of same capacity, as you can see as per the question, 800 picofarad. Okay. This is first one and this is second one. This is the scenario. This is the meaning of the question. We'll come to the numerical later. First, let's focus on what the question says. I have a capacitor, 1. It gets charged with 100 volt battery. Once it gets charged, I'll remove the battery. And now, in between, in the two terminals of the first capacitor, I connected the second capacitor. Same capacitor, 800 picofarad. No battery. So, charges will flow? Of course. Okay. How? We will see. Why? Because of the first chapter, we know that if there are two charged objects, they are in contact with each other, okay, there will be something happening here, right? We'll come to that later. Let's first find, let's call it as V1 or initial potential. So V1 is the voltage across, okay, the first part, which is in the first instant when the capacitor is connected to the battery. So what is the charge gets stored in the first one? So charge will get stored as Q, which is equal to C1 V1. Now what is C1? Sir, 800 into 10 to the power minus 12 into 100 volt. 1, 2, 3, 4. 4 zeros are there. So 8 into 10 to the power minus 8 coulomb. This is the charge that gets stored. Okay. And let's call it as initial charge. Right. Now how much charge is stored across the first and the second when they are connected? We will come to that. So I hope up till here this is clear, that when you connect a 100 volt battery to this first capacitor, it gets this much, maximum charge is this much, not beyond that, because battery itself is 100 volt, right? Now this much charge I am taking and connecting it to the second capacitor. What is our C2 value? Sir, C2 value, let me write here, C2 is also 800 picofarad. 10 to the power minus 12. Let me rewrite it, minus 12 farad. So, this C2 is connected to this one. So, charge, okay, I am assuming, because since here they have taken 800 only, what if in exams they give you a different value instead of 800? Like here, many teachers, they will first say that since they both are 800, so charges will equally distribute. Yes. But what if in exams they change the value by 800 to 600, let's say, or 300, let's say, then what you will do? So focus here. So initial charge is Qi, and finally the charge on this one must be Q1 and this must be Q2. I am doing the general situation. If it is given not 800, if it is 800, we will see that general situation will also come back to this only what I am about to explain. So focus. So Q1 is the charge acquired by the first capacitor, Q2 is the charge acquired by the second capacitor, but one thing is clear, this Q1 plus Q2, that must be equals to the total charge initial Qi. Here, because charges can neither be created nor destroyed, they can be only transferred from one to another system, and if the charge itself in the first one is 8 into 10 to the power minus 8, they can't be more or less than that, they will redistribute. So Q1 plus Q2 has to be Qi. No charges are destroyed or created in between, right? So Q1 plus Q2 is Qi. Great. This is our equation number 1. We'll come back to this. Okay. Now another concept here is, whenever two capacitors are connected, listen very carefully, in the parallel, this is a parallel combination. You are connecting. Sir, what is parallel combination? Let me give you an example from batteries. So if you are going and buying a battery from the market, pay attention. This is the positive terminal. You must have seen that batteries or cells for your clock and all. Okay. So this is plus and this is minus. This is also plus and this is also minus, right? If these plus and plus, they are connected like this, we call it as parallel combination, right? And if you connect like in remote, okay, this is our plus and minus, and you put another battery behind it like this, then this is our series, minus and connected to plus, right? So this is our series combination and this is our parallel combination. So which connection we are doing here for the capacitors? Parallel combination, because we are directly connecting the two terminals. Look here, positive with positive and negative with negative directly. So if they are connected in parallel, their potential must be same, or they should come to a common potential. So voltage across the first one must be equal to the voltage across second one. Will it be 100 volt? No. This time they will adjust their potential in such a way that they will come to a common potential. So voltage across V1 will be equal to voltage across V2. And what is V1? Let me remind you, Q equal to CV. So V equal to Q by C. So what will be the voltage across the first one? It will be the charge across the first one upon the capacity of the first one. And that must be equal to the charge upon the second one upon the capacity of the second one. Correct? Let me repeat again. Voltage is charge upon capacitance. So voltage across the first capacitor must be equal to Q1 upon C1. And voltage of the second capacitor will be charge upon capacitance of the second one. Since in this particular question, C1 and C2 are same, Q1 will be equal to Q2. But if in exams, board exams or any other exams, if C1 is not equal to C2, if C2 is like 200 microfarad or 200 picofarad, then you will be required with this concept. Listen very carefully. So if C1 becomes equal to C2, you can directly cancel them, right? And you left with from here Q1 equal to Q2. This is the reason. The common potential makes it the charges equal here. So since Q1 will be equal to Q2, let's put it here. So I can write it as Q1 plus Q1, because Q2 is also Q1, will be equals to Q initial. So Q1 and Q1, twice of Q1 will be equals to Q initial. So charge across each capacitor will be total initial charge divided by 2. Now you can understand the mathematical way of the same thing, that why the charges are equally distributed, because their capacities are equal. Clear? If their capacitance is different, be very careful, the charges will not be same. So what will be our Q1? The charge across Q1 equals to Q2, and that will be 8 divided by 2, which is 4 into 10 to the power minus 8 coulombs. This is our charge across each capacitor. Clear? If this is our charge and capacitance we already know, can we find the energy stored? Yes. So energy is a scalar quantity? Yes. So energy, the total energy of the system will be equals to the total energy of the first one plus the total energy of the second one. What is U1? So U1 will be Q1 square upon 2C1 plus Q2 square upon 2C2. So this is what, this is again a formula for total energy stored in a capacitor in terms of charge and capacity. Because voltage we don't know, though we can find that voltage, but better is we can directly use, instead of making it more complicated, we can directly find. We already have Q1 values and C1 values and C2 values. Now from here we know Q1 and Q2 are same and C1 and C2 are also same. So we can multiply, because these are two same parameters, we can multiply with 2 into Q1 square upon 2C1. You can also write it here as Q2 square upon 2C2. Doesn't matter because both are same. This cancels with this. Let's substitute the value of Q1 square. 4 into 10 to the power minus 8 into 4 into 10 to the power minus 8 whole divided by C1 capacity. What's the capacity? 800 microfarad. Sorry, picofarad, 10 to the power minus 12. Let's cancel out the terms. 4 2 the 10 to the power minus 8 and minus 8, minus 16. Minus 16 plus 12, minus 4. Correct? And this 4 into 10 to the power minus 4 upon this 200 will be left. So let's divide this. 2 2s are 2 hundreds. Correct? 100, let's take it up. So this will be our final answer. The total energy is 2 into 10 to the power minus 6 joules or 2 microjoules. That is our final answer for this particular question. Great. Let's move to question number 8. Question 8 says, find the total energy stored in the capacitors in the network shown. Okay. So total energy you have to find. You don't have to find the individual, okay, energy across the capacitor. What we will do here, we will first simplify the circuit. Let's start from this corner. So you can see that there is nothing connected between these two wires. So this 2 and this 2 will be in series. Correct? This 2 and this 2 are in series. So let's find the equivalent. So 1 by C equivalent will be equals to 1 by 2 plus 1 by 2. And 1 by 2 plus 1 by 2 is 1. So 1 by C equivalent is 1, which implies C equivalent is 1. Great. If C equivalent is 1, let's call this as point A and B. So across AB, let's redraw it. This is our AB. 1 microfarad. And across AB here also it is 1 microfarad. Here it is 1 microfarad. And here it is 2 microfarad. Okay. So let me just draw it a little up. Now, some students have this confusion, very common confusion. Sir, can I take this 1, 1 and this 1, all three in parallel? No, be very careful. This 2 microfarad is also sitting there. Okay, so these three are not in parallel. But yes, this one and this one, they both are in parallel. Okay, because there is no other capacitor, okay, in between. So this 1 and this 1, that will give you how much? Parallel combination C equivalent will be equals to 2 microfarad. Straight away parallel. So let's draw here across A and B. Let's draw it like this. AB 2 microfarad. Here it is 1 microfarad and here it is 2 microfarad. And from here we have a 6 volt battery which is going like this. Correct? Now pay attention. If you allow the water to flow like this, there is no other option after reaching at point B to go. So it will go, the same water will go across this two. Let me repeat again. If you are allowing to pass water from point A, it will go like this and no other option further. So it will move like this. So same water is going across this two and this two. So this two and this two are in series combination. So let's find the equivalent of these two here. So C equivalent of this 2 and that 2 will be 1 by C equal to, let me write it here, 1 by 2 plus 1 by 2. So 1 by 2 plus 1 by 2, again 1 microfarad, that is our C equivalent. Let's remove these two and let's put here 1 microfarad like this. Correct? So between the two ends we joined another 1 microfarad. Now 1 microfarad and 1 microfarad, what is the equivalent? Parallel combination. So our equivalent capacity of the whole circuit is 2 microfarad. And which is 2 into 10 to the power minus 6. And what is the voltage? So 6 volt. No need of finding the charge. We can directly use the energy formula as half CV square. So this will be equals to half C, which is 2 into 10 to the power minus 6, and voltage, which is 6 into 6. V square, right? So 2 and 2 cancels. You left with 36 microjoules. Done.
Watch the complete playlist on the app Pions. Download the app now.